Welcome to Practical Course number 92, and today we're talking about the effects of tip vortices on airfoils with different aspect ratios. So the aspect ratio is effectively how wide the airfoil is compared to how big the chord is. So we're looking at a paper called The Effect of Tip Vortices on Flow over NACA 4412 Airfoils with Different Aspect Ratios, and you can find the link in the description. And this is important because the tip vortices are not only responsible for things such as the induced drag, and the induced drag is it can be visualized in terms of these vortices, but it's to do with the pressure difference of two surfaces. So the bottom surface typically is a high pressure, the upper surface is a low pressure. So there's a bleeding of air between the high to low pressure because air wants to go from high to low pressure, and that creates this vortex, and it's also a wastage of energy. That's one way of thinking about it. Another way of thinking about it is from a circulation point of view, and this is the greater the change in circulation when you get towards the wing tip, the greater the induced drag. So this is just another way of calculating the induced drag. And the NACA 4412 airfoil. So NACA airfoils are a fairly standardized system of making airfoils, and the 4-digit series, which here we have NACA 4412, so there are 4 digits in there. This ranges a whole bunch of airfoils. So the last 2 digits, typically for all 44-digit airfoils, characterized the maximum thickness, so the thickness to chord ratio, and this means that the thickness is 12% of the chord. The 44 at the front indicates the camber of the wing and where the maximum camber is located. So in this case, the camber is 4% of the chord, and it's located 40% from the leading edge. That second digit, which is a 4, indicates in tenths, percentages in tens, the distance from the leading edge that the maximum camber occurs. So if it's a 4212, the maximum camber occurs at 20% from the leading edge. If it's a 4812, it's 80% from the leading edge. So let's talk about the effects of these wingtip vortices with different aspect ratios. And this is quite interesting because it affects all the flow physics. So they say in these days, one of the studies that looked at the effects of the aspect ratio on the aerodynamic characteristics of wings has been presented by Mizoguchi and Ito, and they first concluded that the influences of the aspect ratio were not as important as they first thought when the aspect ratio is above 3 or more. So that means that the span of the wing is 3 times the chord or more. So it's quite wide. But in this situation, different aspect ratio wings below 3 were significantly affected, and the tip vortices has significant effects on the aerodynamic characteristics on these airfoils. The effects of the tip vortices increased when the aspect ratios of these wings decreased. The maximum lift coefficient and the stall angles considerably increased as the aspect ratio was equal to or less than 1. So in other words, as you reduce the aspect ratio, the maximum lift that you see in these wings and the stall angle dramatically increase, and we'll talk about why that is in a second. And a couple other researchers looked at low Reynolds number flows over different aspect ratio wings for Reynolds numbers of 10,000. So this is important because at 10,000, the flow is most likely going to be laminar. That's not always going to be the case if you have a very turbulent, if you have a very high turbulence density flow ahead. But typically speaking, this is going to be laminar. Once you get to about 200,000, then that's when we get transition to turbulent, generally speaking. And they also found that the stall angle increased significantly when the aspect ratio dropped below 1. And the lower the value of the aspect ratio, the higher the stall angle. In this study, the effects of the aspect ratio on aerodynamic performance is investigated experimentally. After all these tests, the results are compared and discussed with the literature to see if these experimental results are in agreement. So the experimental tests that they did, they printed a NACA 4412 airfoil with different ones with different aspect ratios with a 3D printer, and then rubbed them to obtain a smoother surface of the wing. So this is important because from typical 3D printers, even if you get a good prosumer and even good industry grade 3D printers, they do have roughnesses to their surfaces, and this significantly changes the performance of the wing. The one major reason why that is because these roughnesses, that depending on how you print the airfoil, they could be longitudinal or lateral, and they will turbulate the flow and trigger the turbulence at a lower Reynolds number. So a rougher surface will result in a more turbulent flow, And a more turbulent flow typically results in a higher stall angle because the flow has more energy, which means that as the flow goes along the surface of the wing, it can withstand what's called an adverse pressure gradient. And the adverse pressure gradient is exactly what it sounds like. It's this pressure that's pushing back against the oncoming flow when the flow is going over the wing, and that then decelerates this flow to the point where it will separate. So if you can inject more energy, like higher momentum flow near the boundary layer, in the boundary layer section near the wall, this can overcome this pressure gradient even longer to higher angles of attack, and then you get higher stall angles. So the surface roughness is a big deal, and the reason why they sanded these down is to make them smooth to a certain degree, and that's very good. That's good practice. If you get them straight out of the printer, they're going to be very rough. And trying to compare these with, for example, something coming from a CNC machine, they're going to be very different because the CNC machine is going to be much smoother. And there are ways to characterize the surface roughness if you have, for example, lasers, or you can even do them with scanning, but that's quite advanced. So for the aerodynamic force coefficients of the NACA 4412 airfoil, they have two airfoils, one which has an aspect ratio of 1, and one has an aspect ratio of 3. The Reynolds numbers are 50,000, and they went from 0 degrees all the way up to 45 degrees for the aspect ratio of 1 airfoil, but only up to 28 degrees for the aspect ratio of 3 airfoil. And there's a good reason for that. I'll zoom out a little bit so you can see these graphs. If you're listening to this, you can see the video on YouTube, or you can also see the video on Spotify. So the top graph is for the airfoil with an aspect ratio of 1, so the span is exactly the same as the chord. And in the squares, we have the lift coefficient. On the triangles, we have the drag coefficient. The bottom graph is for an aspect ratio of 3. Now, for the aspect ratio of 3, the stall angle attack is only 14 degrees. What's something to note is that at 0 degrees, both of these airfoils are still producing lift, and that's because this is a cambered wing. So it's a NACA 4412 airfoil, and this is it's a very traditional approximation of airliner airfoils. So like a Boeing 747 or something like that, or 737, they can be approximated by NACA 4412s. Obviously, these airfoils are much more simpler than the airliner airfoils, because airliner airfoils have things like Kruger flaps and wing slats and etc. These ones don't. They're just a simple airfoil, but they're good approximations to in traditional sense, a good first initial understanding of what's going on. So the at 0 degrees, they're both producing lift, and quite a bit of it, about 0.1, is the lift coefficient. And the drag coefficients are non-zero as well. They're actually quite different. For the aspect ratio of 3, the drag coefficient is about 0.1, whereas for the aspect ratio of 1, the drag coefficient is about 0.15, so it's almost 50% more. Why is that? The reason why is because it is a stubbier wing. The aspect ratio is lower, which means that the induced drag is greater. So why does that happen? The reason why is because you have a lot more lift being produced at the wing tip compared to, relatively speaking, over the entire wing. And that means that there's more air bleeding over the vortex. There's more wasted energy when you have a lower aspect ratio. So that's why we get this greater induced drag, which contributes to the overall drag, and that's why we get a greater total drag coefficient. So, however, when we look at the aspect ratio of 1 airfoil, the stall angle is 38 degrees instead of only 14 for the aspect ratio of 3. So in other words, making the aspect ratio much smaller, the stall angle increases dramatically. It's almost 3 times greater than when it's an aspect ratio of 3. So why is that? One of the major reasons is because you have to think about the flow going over the airfoil. So if you have an airfoil just in the wind tunnel and the flow is coming straight on, you might have an angle of attack of 10 degrees, but that is not actually the angle of attack the airfoil will see. So the flow over the rest of the airfoil will affect the oncoming flow as well, in particular the tip vortex. So this tip vortex, it rolls up and down onto the top of the airfoil. What that does is it pushes the flow down, which makes the effective angle of attack, so the angle of attack that the airfoil actually sees compared to the oncoming flow, less, because this oncoming flow now is being pushed down, and that's more aligned with the airfoil's chord. So in reality, the effective angle of attack is lower than 10 degrees, and that's what happens here, because when we have lower aspect ratio, the tip vortex is stronger, which means it's pushing the air much more down into the airfoil, and that reduces the effective angle of attack. Now, there's a second reason why this low aspect ratio might increase the stall angle, which we don't really talk about too much, but I'm going to just touch upon this idea here, and that is that the vortex on top of the surface kind of you can think of as almost like a delta wing kind of setup, where if you have a very low aspect ratio wing, as we have here, only one, so the span is as wide, as great as the chord, the tip vortex is going to be taking up a lot of the span, relatively speaking. So this means that you have a low pressure core on top of the airfoil, which is due to the vortex. The vortex is a low pressure core, and this means that the air going over the airfoil is being sucked onto the surface more. So that's a second reason why the lift coefficient, the stall angle will increase. Now, we don't talk about that too much, but that's one potential reason, especially for these types of airfoils with aspect ratio so low. Now let's look at the drag coefficients. So we get what's called a drag bucket, which is near between 0 degrees and, in these cases, 15 degrees. The drag coefficient is fairly steady. It increases slightly, but it's not too great, the slope. Then once you get to about 18 degrees, they take off dramatically. So for the aspect ratio of 1, the drag coefficient increases dramatically, and also for the aspect ratio of 3, the drag coefficient increases dramatically as well. And this is called the drag bucket. The reason why we get to a point where the drag coefficient starts to increase dramatically is because we start to get separated flow at some point over the airfoil. For the aspect ratio of 3 airfoil, the stall is much more severe than when the aspect ratio is 1. So you can see at a stalling angle of attack of 14 degrees, when we go to 15 degrees, the lift coefficient has already dropped by about 30%. Alternatively, the stall angle attack for the aspect ratio of 3 airfoil is 38 degrees. When we go to 39 degrees, the lift coefficient has only dropped by about 10%, so it's a much more gradual stall. The reason why there is a gradual stall is because of that wing-tip vortex really helping the flow stay attached, both through pushing the flow down and also creating that low pressure core. So the longer airfoil, the aspect ratio of 3, this has a more dramatic stall, and that means that more flow is separated at this point. Whereas for the aspect ratio of 1, the airfoil is experiencing some stall over the airfoil. It usually starts from the trailing edge and proceeds upwards. So it's not like the entire airfoil separates at one angle of attack. It's that it starts at the trailing edge, and then when you start to increase angle of attack, the stall point starts to move up a little bit. So once we get to 38 degrees, most of the airfoil has now separated, at least most of the airfoil that is producing the lift. So that's why we get these increases in the drag coefficient. This is an increase in pressure drag because the wake is at a lower pressure than at the front, which is high pressure, and we have a high pressure compared to low pressure. That results in a net force pushing the airfoil backwards. That's the drag. So we can see now they did some flow visualization to see how these wing-tip vortices are different between the two aspect ratio wings. And they pitched them at different angles of attack, but the ones that I'm interested in are at 24 degrees. So this is for a few reasons. One, this is an angle of attack where the aspect ratio of 1 airfoil is still producing a good amount of lift, but for the aspect ratio of 3 airfoil, the airfoil is undergoing quite a lot of stall. It's not complete stall, but it is a decent amount. So we can see a massive difference in the wingtip vortex here. First of all, it's much larger for the aspect ratio of 1 wing compared to the aspect ratio of 3. And the other thing that we can see is that the aspect ratio of 3 wing, the wingtip vortex actually starts a little bit further up towards the leading edge than the aspect ratio of 1 wing. Now, I'm not exactly sure why that is because the smoke comes at the exact same point, but they didn't go into this paper, but there is a little bit of a difference there. So that's a little bit of an interesting point to make. So they said that in conclusion, the aerodynamic characteristics and corresponding flow structures near the wingtip vortex at Reynolds number of 50,000 has been investigated for 2 wings, for an aspect ratio of 1 and an aspect ratio of 3, and they've been investigated experimentally using smoke wire and force measurements. For low aspect ratio wings, the tip vortices have a considerable effect on the characteristics of the NACA 4412 wing. Now, I should also mention that if you were to have a high aspect ratio as well, you would see that they wouldn't have as great an effect compared to the aspect ratio of 3, but there would still be an effect. And usually what that means is once you get to aspect ratios of about 10 and higher, the induced drag drops a lot. That's why when you get gliders, so airplanes that are very underpowered and usually use thermals to glide, their aspect ratios are usually like 20. And that's because the induced drag plummets. And that means you have a much more efficient aircraft. The lift to drag ratio increases. The lift to drag ratio determines how much glide you can get out of every meter that you drop down. So they only looked at aspect ratios of 1 and 3 because that's going to result in the greatest differences with the wingtip vortices and their effects on the flow physics and lift and drag. But even going above this, you will get a drop in drag, which means that you get an increase in the lift to drag ratios, and that's a measure of efficiency. They said for low aspect ratio wings, the one that had an aspect ratio of 1, the maximum lift coefficient was 1.35 and the stall angle was 38 degrees. Comparing this to the aspect ratio of 3, the maximum lift coefficient was 1.25, so it was about 8% lower, but the stall angle attack was about 65% lower, so that's much worse. So it can be noted that the effects of the tip vortices increase the aspect ratio. The effect of the tip vortices increase as aspect ratio decreases, and this makes sense because the tip vortices, as I mentioned, they affect the oncoming flow, the effective angle of attack, and that affects the lift being produced and the drag being produced. So that's the end of this podcast. Make sure to like, subscribe, and if you have any other ideas you want us to cover in the next podcast, let us know. Otherwise, we'll keep on with our regular schedule. And if you want to get better at theory and or CFD, so we're doing theory here, for example, check out our courses in the link in the description. And if you want to get better experimental results and better CFD validation data, check out MSV Hawk. It makes your experiments 2 to 4% more accurate, which means that your CFD validation data is also 2% more accurate, which means that your validation is more accurate overall. You can trust your CFD more, and that's a big problem these days. So, link in the description for the MSV Hawk, and check out our other podcasts as well. And I'll see you in the next podcast. Peace out, amigos.